Hi everyone, this is Mrs. J, and today we're going to find the derivatives of polynomial and exponential functions. Alright, I have a quick warm-up for you guys, so please pause the video and give it a try. Alright, go ahead and check your work here. So you can see that I use the two different methods using the limit process, so either way is fine. But for the first one, you should get that the derivative of f prime of x is 2x, and for part B, f prime of x is 3x squared. All right, so last unit, like we did in the warm-up, we focused on that limit process to help us find the derivative. So it looks something like this if we were asked to find the derivative of f of x equals x to the fourth. So you guys know that this can be a little bit tedious depending on the function, and it could be kind of time-consuming. So luckily, there are much better and quicker ways to find these derivatives. So this unit, we are going to focus on our differentiation rules to help us find derivatives. So this unit, we would be able to go straight from here to here using what's called the power rule, which is one of the rules we're going to learn about today. So hopefully finding derivatives will become much quicker and easier than in the last unit. However, it is extremely important that you still remember how to use that limit process, because that is the formal definition of a limit, and it really is how all of these differentiation rules are derived. All right, so the first rule we're going to talk about is a pretty straightforward rule. It's the derivative of a constant function. So it says that d dx of c, some constant, is always going to equal 0. So hopefully this makes sense intuitively, because if you have a constant function, it's just really just the graph is a horizontal line, so the slope is equal to 0. And we know that the derivative represents the slope of your function at any given point. So if you have a horizontal line, the slope is always 0, so the derivative is always 0. So again, this is just a definition, but it is pretty intuitive. Here's a formal proof right here. You could do the limit process for this, and it's pretty quick, and you'll end up with that same kind of rule that the derivative of a constant function is equal to 0. All right, the next rule we're going to talk about as far as the derivatives of power functions. So we call this the power rule. So this is going to be an extremely useful rule to us. So here's the general form of the rule. It says that the derivative of the function x to the power of n is simply n times x to the power of n minus 1. So really how I like to envision in my head, you're taking the exponent and essentially you're dragging it out front, and then your exponent just decreases by 1. So if you're taking the derivative of the function x to the power of 5, you drag the 5 out front, and then your exponent decreases by 1, so the derivative is simply 5x to the power of 4. And if you look at the two examples that we did in the warm-up, both of those you could have found the derivative much quicker using this power rule, and you'd get the same answer. So we're going to be practicing this one first, but just like with limits, we have other rules for derivatives that allow us to take the derivatives in these different situations. So first, if you have a constant times a function, you're taking the derivative of that, you can actually pull the constant out front and then just take the derivative of the remaining function and multiply by the constant at the end. So for example, if you have the derivative of 3x to the fourth, you could really just take the derivative of x to the fourth, which using the power rule would be 4x cubed, and then multiply by that constant of 3, giving you 12x cubed. So that's our constant multiple rule. We kind of use that a lot, really, without even really defining that we're using that rule. It'll kind of just become second nature to you. And next is the sum and different rules. So if you're taking the derivative of the sum or difference of two different functions, you could take the derivatives individually and then take the sum or difference of those derivatives. So again, these are kind of intuitive rules. We don't necessarily state that we're doing them every single time, but these rules do allow us to take the derivatives of a lot more situations. All right, so let's try a couple examples together. So we're going to find the derivative of each of these functions. So for this first one, we can use that power rule. And we're going to also kind of use this in combination with those other two rules that we just talked about, the constant multiple rule and the sum and difference. So we're really just going to take the derivative of each individual term separately. So f prime. So here, I'm going to take the exponent, I'm going to multiply it out front. So this becomes 18, and then my exponent decreases by 1. So again, that's that constant multiple rule in combination with that power rule. And then here I'm going to take the 4, multiply it to the negative 5, and then my exponent decreases by 1. Here my exponent is 1, so I multiply it to the number out front, which is 7. And when my exponent decreases by 1, it just becomes 0. And then here you can imagine this, if it helps, as x to the power of 0. So if you take the exponent of 0 and you multiply it to the constant, this term just becomes 0. So we no longer have that fourth term. And this is our derivative. So much, much, much quicker and easier than using that limit process that we did last unit. All right, let's look at this next one together. Here we have 2x cubed minus 7 times the square root of x. So it might be useful to rewrite that radical term to have a rational exponent. So then we could use our power rule. So g prime of x, so we multiply the 3 to the 2, and we drop our exponent by 1. So it becomes 6x squared. And then we multiply the 1/2 to the negative 7. So negative 7 halves. And our exponent still decreases by 1, so it becomes x to the negative 1/2. And then typically we don't leave our final answer with negative exponents, so we can just simply rewrite this as 7 over 2 times the square root of x, or 7 over 2 times x to the 1/2. Either way is fine, and that's our derivative. All right, let's try 2 more together. So here I know this looks strange because our derivative or our exponents are kind of weird decimals or fractions, and some are negative. We can still just use that same power rule that we used in the last example. So here y prime is going to be 3.2. So you take the exponent and you multiply it out front, and then our exponent is still just going to decrease by 1. So it just becomes t to the power of 2.2. And then here, the negative 1.8 multiplies to the negative 1, so it actually becomes positive 1.8. Then again, we just subtract by 1 for the exponent, so negative 2.8 is our new exponent. Then we have plus 3/4, and then we have t to the negative 1/4. So again, I'm just following that power rule. My exponent is decreasing by 1. Here we wouldn't leave our final answer like this due to the negative exponents. So we're just going to rewrite it as 3.2 times t to the power of 2.2 plus 1.8 over t to the power of 2.8. And last, 3 over 4 times t to the power of 1/4, or 0.25, or you could do the fourth root of t. Typically, if the original problem has a rational exponent, we can match our answer to that same form. So this is our derivative, y prime. Let's do one more together. So here we have s of r, and I know this doesn't look like the typical power function, but we can actually rewrite it. So we'll simply divide each of these terms by r to the 4th. So we have individual terms with exponents. So we have r squared minus r to the 5th plus 7r to the power of negative 1. And then from here, this is going to allow us to use our power rule. So s prime of r is 2r, and then it's going to be r to the power of 1. So I'll just leave it as 2r. And then we have minus 5r to the power of 4. Remember, I multiplied this out front and I subtracted 1 in the exponent. And then here we have minus 7, and then it becomes r to the power of negative 2. So remember, we are subtracting 1, not adding 1, so it doesn't become 0. And then last, we do want to make sure to get rid of that negative exponent for our final answer. So we have 2r minus 5r to the 4th minus 7 over r squared. All right, so at this time, go ahead and pause the video and give these two a try on your own. All right, go ahead and check your work here. So for part A, pretty straightforward power rule. Do remember that this term will actually disappear because it's x to the power of 0. So that 0 multiplied to the 3 makes it disappear. And for part B, it is helpful to first rewrite this as x to the power of 1/3, and this is x to the power of 1/2, and then you just use your power rule from there. All right, the last rule that we're going to talk about today is the derivative of the natural exponential function. So that's your base e functions. And this, we like to say, is the easiest function to memorize the derivative for, because the derivative of e to the x is just e to the x. So just remember, it is easy. And it's actually the only function that exists where the derivative is itself. So that e to the power of x is actually a pretty cool derivative. So we are going to look at a quick proof of this rule, and to complete that proof, we do need to know this formal definition of the number e. So e is a number such that the limit as h approaches 0 of e to the power of h minus 1 over h equals 1. So just make note of this because we are going to use this definition in the proof that we're going to do on the next slide. All right, let's give this proof a try together. So we're finding the derivative of e to the x using our formal limit process. So we'll do the limit as h approaches 0 of e to the x plus h minus e to the x all over h. So we can't use direct substitution yet, so we need to do a little extra work. And in the numerator, we can actually factor out e to the power of x. So when you're factoring out, we're really just dividing each term by e to the x. So when we divide it out from this first term, just remember all you're doing is subtracting your exponents. That's our rule for dividing. So it's e to the x plus h minus x. So when we factor it out, what we're left with is just e to the power of h. And then here we're just left with 1 all over h. Now from here, you might notice this portion of our limit is that definition that we had on the previous slide. So just by definition, the limit as h approaches 0 of e to the h minus 1 over h is just equal to 1. So all of this is simply equal to 1, and then that just leaves us with the remaining e to the x. So we've just shown that the derivative of e to the x is just e to the x using our formal definition. All right, so now let's try using that rule that we just learned. So here we have f of x is equal to e to the x minus x, and we want to find f prime and then f double prime. So we'll start with that first derivative. So we're going to start just by taking the derivative of this first part of our function, and the derivative of e to the x is just e to the x. And then we could take the derivative of this second part using our power rule. So the exponent is 1, so we multiply it out front. And we're left with x to the power of 0, so the variable disappears. And this is our first derivative. And then we also need to find the second derivative, so we're going to take the derivative of f prime. So the derivative of e to the x is just e to the x, and the derivative of -1, that's our constant derivative rule, it's just 0. So f double prime is simply e to the power of x. All right, so go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. Our g prime should be 2e to the x minus 6x, and then g double prime should be 2e to the x minus 6. All right, let's try another one together. Here we're going to find the equation of the tangent line and the normal line to the curve y equals x root x at the point 1, 1. So we know what a tangent line is, but just a quick recap of what a normal line is. A normal line is a line that is perpendicular to the tangent line at any given point. So it's perpendicular to the tangent line. And hopefully remember that perpendicular lines have slopes that are opposite reciprocals. So we'll need to remember that to help us make the equation of the line. All right, so let's start by finding the equation to our tangent line. So we know that to find the equation of our tangent line, we're going to need to find the derivative when x is equal to 1 because that will tell us the slope of our tangent line. So to find that derivative, it might be useful to rewrite our initial function as y equals x to the 3/2. So we can use that power rule to help us find our derivative. So it's 3/2 times x to the power of 1/2. So if I substitute x equals 1, it will tell us the slope of our tangent line at x equals 1. So we can show this by doing a vertical line and saying x equals 1 at the bottom right. It just tells what we're evaluating. So 3/2 times 1 to the power of 1/2 equals 3/2. So this is the slope of our tangent line, and we know that it goes through that point 1, 1. So now we can make the equation of our tangent line. So we use the point slope form. So y minus y1 equals m times x minus x1. So you can leave your answer like this, or you can rewrite it in slope-intercept form. Either way is fine. All right, so that's our tangent line. So now let's do our normal line. So it's still going through that same point, 1, 1. However, the slope is going to be the opposite reciprocal of the slope of our tangent line because they are perpendicular. So for this one, our slope is going to be negative 2/3. But again, it's still going to go through that same point of 1, 1. So we could do point slope form again. So y minus y1 equals m times x minus x1. And again, you can leave your answer like this, or you can rewrite your equation in that slope-intercept form. Both are correct. So again, here we're using that derivative to help us find the slope of our tangent line at any given point. So here it was when x is equal to 1. And then to find the slope of the normal line, we simply take the opposite reciprocal of the slope of our tangent line. All right, let's try one more together. So here we're going to find the points on the curve y equals x to the 4th minus 6x squared plus 4, where our tangent line is horizontal. So first we need to kind of interpret what are they really asking us to find. So we want to find the points if our tangent line is horizontal, that means that y prime is 0. The horizontal lines have a slope of 0. So that means first we need to figure out the x values where our derivative is equal to 0. So that means we first need to find y prime. So we could do our power rule for this. And we get 4x cubed minus 12x. And then again, we need to figure out where our derivative is equal to 0. So we're just going to solve. So this one we can actually solve by factoring. And then doing zero product property. So here we get x equals 0. And then here, remember we do need to take the plus or minus square root of both sides. So it's plus or minus square root of 3. So there's actually 3 times when this graph has a horizontal tangent line. So we do need to find the entire point. So we have the x values of our points here, but again, we need to know the entire coordinate. So to do that, we simply just need to plug in these x values into our original function. So first, let's plug in when x is equal to 0. So we get 0 to the power 4 times 6, minus 6 times 0 squared plus 4, which equals 4. So one of our coordinates is 0, 4. And then we need to plug in plus or minus square root of 3. So let's start with the positive. So we have square root of 3 to the power of 4 minus 6 times the square root of 3 squared plus 4. And if you simplify that, we should get 9 minus 18 plus 4, which equals negative 5. So we have the point root 3, negative 5. And if you plug in the negative square root of 3, you'll actually get the same answer because both of your exponents are even. So that's also negative 5. So you have the coordinate negative root 3, negative 5. So you can see that now that we know a couple of our rules, especially that power rule, it's much, much easier for us to complete problems like this because now finding that derivative is just a much quicker and smaller step, kind of allowing us to do a little bit more with our problems. All right, so I have one last one for you to try on your own, so pause the video and give it a try. All right, let's go ahead and check your work here. So here's our derivative, y prime, and then we want to know where the tangent line is horizontal, meaning where our derivative is equal to 0. So we can solve for this just by factoring. We get two x values, but again, we want the points on the curve, so we just go back and plug those in to find the entire coordinate. So I do want to point out here we're finding when the tangent line is horizontal. I just want to remind you guys, if you're wondering, what about when the tangent line is vertical? Can this ever happen? And I want to remind you that this never, ever, ever happens. When we have a vertical tangent line, our derivative, it doesn't exist. Our derivative is not defined. So it's never defined if the tangent line is vertical. So we're really only going to be working with times when the tangent line is horizontal. All right, so here's just a quick recap of the rules that we've learned so far. We're going to be learning a lot of different rules this unit, so I just want to kind of keep track of what we know, and I do want to encourage you guys to maybe start making flashcards now. So by the end of the unit, you have a whole set of all of the different differentiation rules that you need to know. All right, so that is all for today's video. Thank you so much for watching.